So now that we know how to take the derivative of a function from Rn to Rm, so that is to take the Jacobian derivative, which is an m by n matrix, let's talk about how we can actually use that object. And unsurprisingly, if we think about Calc 1, one of the main interests is linear approximations. That's what we use the derivative for often. And so we will use the Jacobian derivative to construct what's called the local linearization of a function from Rn to Rm. So by definition, the local linearization of a function f from Rn to Rm at a point P in the domain is defined as L sub P of x equals f of P plus df of P, so that's the Jacobian derivative of f evaluated at P, times the difference vector x minus P. Now, the point of studying the local linearization is to approximate the function f when the input is near P. So much like in Calc 1, what we do is we use the local linearization to approximate f of P plus a vector delta P. So the approximation is f of P plus delta P is approximated by the local linearization evaluated at P plus delta P. And if I go to my formula for local linearization, what I'm doing is I'm replacing my input vector x with P plus delta P. The only place that x appears is in this last part where I'm taking x minus P. So I'm now looking at f of P plus df of P times P plus delta P minus P. And the key thing here is that the p's cancel as vectors. And what I'm left with is f of P plus the Jacobian derivative of f evaluated at P times delta P. So this is the idea behind linear approximations. If you know what your original output of your function is, and you know what the Jacobian derivative at that point is, when you deviate from the original input, you can use this as an approximation of what the new output of your function is. So let's look at some examples. So here I have a function of two variables, f of xy equals negative 5xy minus y and negative 10x minus 3y. So this is a function from R2 to R2. Now let's see what happens when I plug in the value x equals 1, y equals negative 2. I replace x equals 1 and y equals negative 2 in my coordinate functions, and I see that this function spits out the vector 12, negative 4. So that's the initial output of my function if I'm focused on the original input 1, negative 2. Then I could calculate the Jacobian derivative of this function. Again, this is a function from R2 to R2, so when we construct the Jacobian derivative, we build a 2 by 2 matrix. And then what I'm going to do is I'm going to plug in my original input, 1, negative 2, into this Jacobian derivative. So I'm replacing my x's in the Jacobian derivative with x equals 1, and I'm replacing my y's with y equals negative 4. So that produces this specific Jacobian derivative, whose columns are 10, negative 10, and negative 6, negative 3. So how could I use this to approximate something? Well, let's say now that I wanted to deviate from x equals 1 and y equals negative 2 and approximate the new output. So let's say that I'm looking at f of 1 minus 1/10, comma, negative 2 plus 1/3. So the idea here is that the approximation should be given by the original output, so that's f of 1, negative 2, which is 12, negative 4 as a vector, plus my Jacobian derivative evaluated at the original input, that's this 2 by 2 matrix we just constructed, multiplied by my change vector, which is keeping track of how the coordinates change under this new input. So if I started at 1 and I'm subtracting 1/10, the first coordinate of delta p here should be negative 1/10. In my second coordinate, I started at negative 2, and now I'm adding 1/3, so the second coordinate in my change vector, delta p, should be 1/3. So now when I do this arithmetic here, I take 12, negative 4, plus my 2 by 2 Jacobian derivative, times this delta vector, I end up with a new vector, which is 9, negative 4. So that gives me my approximation of f at this new input, which is represented as a deviation from the original input, 1, negative 2. Here's another example. This is an example of a function g of two variables, which has three outputs. So the original input I'm going to use here is x equals 1, y equals negative 1. When I plug in x equals 1, y equals negative 1 into this function, I produce the coordinates 0, 1, negative 1. So that's the original output of my function if 1, negative 1 is my input. Then I'm going to calculate the Jacobian derivative of this function. This is a function from R2 to R3, so its Jacobian derivative is a 3 by 2 matrix. Now I'm going to plug in the value x equals 1 and the value y equals negative 1 into my Jacobian derivative, and I produce a specific matrix. Here the columns are negative 1, 1, negative 1, and 1, 0, negative 3. So now I can use this data to approximate what would happen to the output of this function if we deviated from x equals 1 and y equals negative 1. So let's say that I wanted to approximate the value of g of 1 minus 1/3, comma, negative 1 plus 1/4. So now I'm deviating from the original x input by negative 1/3, and I'm deviating from the original y input by 1/4. My approximation says I should take the original output, which was 0, 1, negative 1, and then add the Jacobian derivative evaluated at the original input, which is this 3 by 2 matrix, multiplied by my change vector, which is negative 1/3, 1/4 in this example. When I do all my arithmetic here, I get my approximation, which is this new vector, 7/12, 2/3, 1/12. So this is how we use matrix arithmetic to approximate outputs of functions in multivariable calculus.